Rise AI enables a direct path from high-level design specifications to synthesizable System C with matchlib code, dramatically reducing the manual effort required to build complex hardware systems. What makes that possible is not just a general-purpose LLM, but a system grounded in Rise-specific agents, reusable skills, and a knowledge base of canonical design examples. These include standard integration patterns, established coding conventions, and reference IP such as the Rise Axie managers, stream converters, and control plane building blocks. With that context, the model can reason about how to assemble real HLS designs in a way that matches Rise's expected architecture and coding style. Instead of handwriting control logic, interface glue, and top-level interconnect, you describe the architecture and interfaces in a spec form, and Rise AI uses that combination of domain knowledge and generation capability to produce a complete connected design. In this example, we'll walk through how a Sobel Edge Detection pipeline is constructed, from a control specification through top-level integration, all the way to code that can be compiled with Rise HLS to generate RTL, automatically verify correctness, and estimate power, performance, and area. We start with the control specification, which defines the software interfaces, MIMO registers for image size and Axie parameters, along with the go signal that drives execution. From this spec, Rise AI automatically generates a synthesizable System C control block, including the Axie write slave, register storage, configuration wiring, and start signal fan-out to each stage of the pipeline, eliminating the need to manually implement control logic or register maps. Here's the top-level spec. The goal is to integrate existing IP, the control that we generated, the Sobel stages, and Axie read-write masters into a single System C module running at 1 pixel per clock. At the top level, we expose clock, reset, done, and Axie interfaces. The result is a clean top-level integration that stitches together pre-built IP using standard Rise and matchlib interfaces. Rise provides RDA Analyzer, a VS Code extension, to allow designers to perform detailed analysis of the synthesized design. Let's go ahead and walk through the Edge Top design that we synthesized previously. Edge Top contains multiple synthesized modules, and the instance report shows that the magnitude angle is about 90% of the design area, not including memory area, and we'll see why this is in a moment. Zooming into the vertical gradient, this is where the line buffer memories live. The design infers 2 single-port RAMs, linebuff0 and linebuff1, each holding a full image row. These are marked with the HLS RDA memory pragma, which causes the arrays to be inferred as memories. Magnitude angle is where the heavy math lives. It computes a square root using the AC math library piecewise linear approximation and an arctangent using the AC math Cordic implementation, which is why this block has 12 pipeline stages as its iteratively rotating vectors over multiple cycles. Despite the complexity, the design is still able to achieve 1 pixel per clock throughput. In the same fashion that we generated the RTL from a spec, the Edge Top test bench is also generated from a test bench specification along with the generated HLS design. The test bench loads an input image, programs a DUT through the memory mapped I/O, and waits for completion. Afterward, results are read back and compared against a software reference. We then automatically run RTL co-verification using the generated RTL and the same System C test bench. This works because HLS produces verification adapters with transactors that bridge pin-level RTL to high-level transactions. Once RTL is generated along with the test bench, co-verification is executed using the System C test bench to validate the design end-to-end against the reference model. At the same time, the simulation gathers performance statistics tracking data movement through the interfaces to measure effective I/O throughput. This allows us to confirm not just functional correctness, but that the implementation meets the throughput and bandwidth targets defined in the specification. This demo demonstrated 3 key points. First, Rise takes you from spec to production-ready RTL automatically using a deterministic AI architecture. This means real implementable hardware, not just generated code. Second, our AI is built for hardware. Every decision is grounded in domain knowledge and validated by real tools, so what you get is silicon you can trust. And third, it's fast and fully transparent. We're 30 to 100 times faster than traditional approaches with deterministic results and full visibility at every step. So the takeaway is simple: faster path from spec to silicon with confidence built in.